Okay, everyone, welcome to lab 1. In this lab, we're going to be looking at the behavior of a non-inverting amplifier. So what we're going to do first of all is we are going to take our circuit here, which has a non-inverting amplifier at the top of it, and at the bottom an inverting amplifier, which we'll look at in a different lab. And we are going to supply a voltage to this non-inverting amplifier and see what it does at the output of it. To do that, we are going to use our DC power supply. What we are first going to do is characterize the performance of this non-inverting amplifier across a range of voltages. There's a couple of ways we could do this. One is that we could use our power supply here and change this input voltage. That would work just fine. However, as a good demonstration of another method, we are going to instead use this fixed output here and combine that with a potentiometer. Remember that a potentiometer acts as effectively a variable resistor. So that way, by changing the setting of the potentiometer, we can change the voltage we are then supplying to the circuit. What we are going to be doing in this experiment first is we are going to supply a positive voltage from 0 to 5 volts to the non-inverting amplifier. We're then going to turn that around and supply a negative voltage from 0 to -5 volts to the non-inverting amplifier as well. Okay, so first of all, for our positive 5 volts or 0 to 5 volts, we want to make sure our fixed output is at 5 volts, which it is. This has an option to switch between 3.3 and 5 volts. We can then connect our potentiometer so that the positive red connection is to the positive output and the black or ground is to the negative. That will supply power to the potentiometer. We then are going to supply that into the circuit using, in this case, this blue wire will supply to the circuit and this black one is ground. So we will hook this blue wire into the non-inverting input, which is a screw terminal. So you push the wire in and screw to clamp it down. And same for the ground terminal as well. Now, the device we're using in this non-inverting amplifier is an op-amp, an operational amplifier. An op-amp needs to have power supplied to it. It needs both a positive and a negative power supply, as well as a ground supply. So this is another reason to use this fixed supply to supply voltage to our circuit, so that we can then use the other two terminals, these variable ones here, to supply power to the operational amplifier. For this operational amplifier, we want plus or minus 15 volts. So I want to set up both my supplies. I'm going to set them both to 15 volts and that 100 milliamp current limit. Okay, so they're both set at 15 volts and 100 milliamps. We then want to connect that into our operational amplifier circuit. You'll notice at the top of this board, there is a 3-pin header we can plug in to supply that voltage to the amplifier. So to connect up our supply positive 15 negative volts to our amplifier board, we want to use, in this case, this particular cable here. This has 3 banana plugs on one end, so we can plug in the 3 required connections. And the other end has this 3-pin header connections that we can plug that in to the header on the amplifier board at the top here. So what I'm going to do is I'm going to plug that in. You'll notice that it has a little key on it, so it only goes in round one way, so you can't put it around the wrong way. Plug it in. We want to follow our general color code conventions, where we usually have red as our positive supply, black as our negative supply, and green as ground. So I'm going to arbitrarily use this left-hand supply as the positive 15 volt supply, the right-hand one as the negative 15 volt supply. You could do it around the other way too, it doesn't really matter. So positive 15 volts, plug this red banana clip into the red terminal, the positive terminal of this power supply, and plug the black one into the black terminal of this power supply. And I plug the ground connection. In this case, I'm going to use this far right terminal here that I briefly mentioned in the last lab. I'm going to plug it into here. This terminal here is our earth reference, which we're going to use in a moment. What we now need is to make sure that both of these supplies both provide plus or minus 15 volts with respect to the same ground. Here it's important to remember that voltage is a potential difference. It is a difference between 2 points. Currently, this is 15 volts between these two terminals. This supply is also set to 15 volts, but between these two terminals. So there could be any voltage between these two. We don't know. This could be 30 volts above this terminal, for example. We don't know, unless we give them a common ground. So what we need to do is say, well, this is our positive 15 volt terminal. What I'm going to do is connect the negative terminal here that we're not using, which is usually our ground reference. And I'm going to connect that to the positive terminal of our negative 15 volt supply. So let's say that again. I am connecting the unused terminals of either side to each other. That way they are both at the same ground or 0 volt reference. So plug them into each other like that, which is what this wire here is for. Lastly, I am going to connect them to the earth connection over here on the right hand side of the power supply. I do this for 2 reasons. One, so that the ground that is supplying the op amp on this board is at the same voltage as the ground for these supplies. And 2, because earth is generally a nice stable ground reference. If I have these two connected to each other, they are probably at the same ground, but that could vary a bit. By connecting them to earth, I have a much more stable ground connection. To do that, I'm going to use another banana to banana plug. And I'm going to plug them into the top of these plugs. You notice there's a little hole there. These holes, so you can plug them into each other. This hole here has a little metal cylinder in it so that it is conductive. So I can plug this banana clip pin into there, and likewise into either one of these. Remember, this wire is connecting these two terminals together, so I don't have to plug them both in to earth. Okay, so now our power supply is set up. So we have positive 15 volts at this terminal, negative 15 volts at this terminal, and a fixed 5 volts in the center here. What we are now going to do is we are going to measure the input and output voltage from this circuit. That way we can say for a given input supply, how much output do we get? To do that, we're going to need to use 2 multimeters, one on the input and one on the output. Again, we're going to need appropriate cables for these multimeters. So we're going to use the banana to alligator clips so we can hook on to measurement points. And we are measuring a voltage. So again, we want to use the voltage in common terminals. And that's the case for both multimeters. What I'm going to do is I'm going to hook the negative clip, the common clip, to this rail here, which is connected to this ground reference on the board. So you see that metal rail there, that is connected to this ground here. I could also try and clip it onto here, but it's a bit more fiddly. And I'm going to clip the positive end onto where my positive voltage supply is coming in, which is through here. That screw terminal there, which I am going to clip onto. Likewise, on the output side, I hook on my common reference, my ground reference, onto that common or ground rail, and my positive clip onto the output terminal, which is this terminal here, labeled non-inverting output. I'm going to hook it directly to that terminal. You'll notice a couple of things. One is that there is nothing connected to the output. So the moment I'm connecting, I'm measuring the output with no load upon it. And we'll look at the effect of loading a bit later. The other thing is that if you find this terminal difficult to hook up to, or you in general find a connection difficult to hook up to, you can use a short length of wire to help you with that. So I can put a short length of wire in here and hook on to the other end of that, if that makes things a bit easier. It's worth noting at this point that we do have quite a few wires around, and so this is a good indication of why it's important to take your time with this, set it up as clean as you can, use wires that are appropriate length, and use some kind of color coding convention. It makes it a lot easier to see what's going on. Now that everything is set up, I'm going to set both of these multimeters to measure DC voltage. On the input side, I know I've got up to 5 volts, so I'm going to put that on the single volt range. And on the output side, I'm going to start in the single volt range and adjust that as I need to. So this is our input, this is our output. We can see at the moment our input is at 1.251 volts. I can change that using the potentiometer here. If I dial that around, I can turn that down or up. We're then going to take measurements at each voltage step. So 1 volt, 2 volt, 3 volt, 4 volt, 5 volts. So I can set it to 1 volt. The one other thing I need to remember to do is to make sure I turn on the outputs of the power supply so that this circuit has power. You'll notice that moment measuring 0 volts in output. That's because there is no power here, so this can't amplify. This can't amplify anything. So I turn both of my outputs on. I need both of them on. I can see this is out of range, so I change it to be in range. And for a 1 volt input, I measure 4.31 volts at the output. I can then change the potentiometer to measure that at different voltages. To then measure with a negative input voltage, what I can do is I can turn around the connections I have for the potentiometer here. So currently I have the positive connected to the positive and the negative connected to the negative. If I flip those around, it becomes a negative voltage. So I will do that now. If I do that, I can then supply a negative voltage into the circuit. Again, I can vary what that voltage is with the potentiometer. You can see it reads that as negative. And you'll see that for that in this circuit, I get a negative output as well. And again, there is some amplification going on there. Again, we can measure that at various voltages to get the appropriate values. Once we've taken those measurements for each voltage from 1 to 5, we also want to measure the output of the circuit at 0 volts in the input. In principle, we can use the potentiometer and dial the input voltage all the way down to 0. But that's only 0 to within some appropriate accuracy of this circuit. To be more confident that we do have 0 volts and only 0 volts at the input, what we can do is instead disconnect this potentiometer from the circuit. And instead use a short length of wire, such as this, to directly connect the input and ground terminals together. That way there should be exactly 0 volts at the input. So I'll quickly wire that in. Now we know we have 0 volts to the input. We need to be a bit careful with how we measure the output voltage then. At the moment it is showing 0. However, if we change that down to a more sensitive range, we will start to be able to see some actual measurements. So if you're trying to measure something that could be quite small, be aware you may need to change the range on your measuring device. Okay, so that's how we can characterize the behavior of the amplifier with different inputs and outputs. Our next task is to measure the input impedance, the input resistance of this circuit. So for table 1.1, this is the input side, this is the output side. Take note of what the output voltages are for each input voltage. Currently, this is set to positive 1 volt. I will dial that up to positive 5 volts. I'll then go from negative 1 volts to negative 5 volts and also show the recording at 0 volts. So this is for 1 volt input, we get 4.36 volts at the output. For 2 volts input, this is the output. For 3 volts input, there is the output. for 4 volts input. There is the output. And for 5 volts input. I now do that for the negative voltage range. So for negative 1 volt in, we have a negative 4.34 volts out. That is negative 2 volts input. Negative 3 volts input. Negative 4 volts input. And negative 5 volts input. Finally, for 0 volts, I will short the 2 input terminals together. And I will change the range on the output side multimeter to get a more accurate measurement. So that is the measurement in millivolts for the output voltage with an input of 0 volts. You should be able to use that data to complete table 1.1 and the associated questions. Next, what we want to do is measure the input resistance of this circuit. So we know that every circuit will have some resistance, and we can think of this circuit as a black box with some input resistance, some internal stuff it does, in this case amplification, and some output resistance. We cannot measure what those resistances are directly because they are part of this circuitry. Instead, we have to think of it as a black box, measure what effect they have, and therefore infer what those resistances are. To do that, what we're going to do is take a known resistance. So in this case, we are going to take a 4.7 kilo ohm resistor that I have here. And to be sure, we are going to measure the resistance of this resistor so that we can be confident that it is 4.7 kilo ohms. So we can see this resistor has a resistance of 4.65 kilo ohms, so approximately 4.7. And we can note down what that resistance measurement actually is. What we can then do is use this resistor and following the diagram shown in figure 1.7b, hook it up as a known input resistance. By then measuring the currents that flow, we can determine what the input resistance of the circuit is. So what we're going to do is use our potentiometer to supply 1 volt to the circuit. You could use a different voltage. Doesn't matter too much. It does matter that you know what the input voltage is. In this case, for simplicity's sake, we are going to supply 1 volt to the input of this circuit. So I hook up the potentiometer to the input of the circuit, and I measure that voltage so I know that it is 1 volt, and I will need to vary the potentiometer to make that correct. So I can dial that potentiometer until we get to 1 volt. You'll notice that we may not be able to get it to exactly 1 volt. There's only so much precision we can do. We get as close as we can, and then we record what we actually get in practice. So we've got basically 1 volt input now. What we want to do, according to figure 1.7, is supply that 1 volt into our known load. So in this case, our 4.7 kilo ohm resistor, and then supply that in turn into the circuit. To do that, what I'm going to do is I'm going to use a crocodile clip to crocodile clip cable. So I will take the blue wire supplying from the potentiometer and hook on one end of this crocodile to crocodile clip cable to it. The other end I will hook onto one leg of this 4.7 kilo ohm resistor. The other leg I will plug into the circuit input. Now take note, when we're measuring that 1 volt, look carefully at figure 1.7b. We are measuring that 1 volt on the input side before we reach the input of the circuit. If you measure on the other side of the resistor, you'll get a different value, which we should expect, as the resistor should cause a voltage drop. So we want to measure 1 volt before we reach the resistor, and then measure the voltage we get afterwards. So I may need to readjust the potentiometer so that we have 1 volt at the input. Knowing that we have 1 volt at the input, we can then measure what is labeled as V in on figure 1.7. That V in, note carefully, is the voltage after the known 4.7 kilo ohm resistor. If we measure that, this is the voltage we get. So knowing that, we can determine how much current is flowing through the resistor, and then therefore we can determine the input resistance of this circuit. Next, what we want to do is measure the output resistance of this circuit. So again, we can supply a known 1 volt to the circuit, again, using the potentiometer. Again, make sure you measure it to ensure that it is 1 volt. So I'll hook the potentiometer back in directly into the circuit. So removing that 4.7 kilo ohm resistor. And I will measure that voltage and make sure it is set to 1 volt by adjusting the potentiometer as required. What we are then going to do is use a known load resistance in the circuit. In this case, we're going to use a 1 kilo ohm resistor. So we'll grab a 1 kilo ohm resistor, and again, we will measure its resistance to be sure that it is 1 kilo ohm. Using this multimeter, I will measure that resistance. And I find it is 993 ohms. So essentially 1 kilo ohm. That is on this meter, by the way. So now we know for sure what that resistance is. What we are going to do is take a measurement of the output voltage of the circuit when we apply this 1 kilo ohm as a load to the circuit. So if you look at figure 1.8, The schematic shown in part B of that figure shows you how we're going to do this. We apply this resistor to the output of the circuit so that current flows, and a voltage drop is caused by both this known resistance and the unknown output resistance of this circuit. By comparing that between the loaded and unloaded case, we can determine the output resistance of the circuit. So I take this known load resistor and I connect it between the output terminal of the circuit and the ground terminal of the circuit, thus causing a current to flow through this resistor. So I can hook that up like so. You can see the resistor plugged in here between the non-inverting output and the ground terminal. We then measure the voltage drop across that resistor using our multimeter. So I'm going to do that by hooking onto the two terminals that we're connected between and measuring the voltage. Doing so, we measure an output voltage of 3.94 volts. So with 1 volt input and with a 1 kilo ohm load, we have 3.94 volts out the output. Using that, we can determine how much current is flowing through that resistor. We can then use the data we recorded earlier in table 1.1 to say, well, we know what the output voltage was when there was no load. We now know what it is with a load. We can therefore work out what the output resistance of the circuit is. Okay, so now we have measured the gain of the circuit and how it behaves, and we have measured the input and output resistances of the circuit as well. The last thing we are often interested in, which I'll go over here, is what is called the offset voltage of an amplifier. The idea is that in principle, if we have nothing connected to the input of the amplifier, nothing should happen. There should be 0 volts there. However, in practice, we find there is some small non-zero voltage there, which we want to be able to measure. This can be quite significant, seeing as we have a current limit in the circuit. If we have some small input voltage, they'll get amplified at the output to become a larger output voltage. If we then connect that to a load, that output voltage will cause a current to flow. If that current is close to or exceeds the maximum current the circuit can provide, we will not be able to use this circuit as we expect. So if you refer back to table 1.1, where we measured the output voltage at 0 volts, you better know what the what we're calling the offset output voltage is. What we can then do is, by considering the figure model and shown in figure 1.9, we can say that we've got some input and some output and a gain between them. Given that we know what the output was and the gain of the amplifier, we can therefore determine what the input voltage was that caused that output. So we assumed it was 0 volts. We're going to measure what it actually is. And then finally, knowing the size of that input voltage and knowing the input resistance of the circuit, we can determine how much current is flowing to cause this input voltage to arise, what we call the parasitic input current. That is all for lab 1.